now we finally have a chance to look at this issue of the whole picture of mechanics of polymers. So if you open any textbook, we are really puzzled by the fact that the intrinsic strength is always 100 times larger than nominal strength. Many textbooks will say the same thing. So today, I'm hoping to answer a few questions related to that. So in fact, these three main questions are whether the inherent strengths are actually comparable to the nominal strength. In that case, the fracture behavior of uncut polymers really is not a fracture mechanical problem. And I will also try to show and convince myself I understand why and how fracture mechanics works for polymers when you have large cut. And then lastly, I hope through our work, I could show you that when you consider fracture mechanics, there may be an alternative way to think about toughness. Okay, so toughness in the sense of us usually attributing fracture strength to critical energy release rate. So this was done, of course, without my student, nothing can be done. 3 of my students and sponsored by NSF. So very quickly, I just want to orient myself by saying I'm fulfilling my dream, trying to understand just all aspects of mechanical behavior of polymers from liquid state, where I think we understand it at least qualitatively very well. And then when you cool down to solid state, glassy or semi-crystalline, we have been working on that. Not complete, but we have some significant understanding there, which allowed us to look at the problem of fracture mechanics. So just let me repeat the same thing. For plastics or elastomers, it's textbook description that we typically find the ultimate strength to be much higher than what we observe, both for plastics and for elastomers. We'll discuss why this is, what happened. Not everyone perhaps is a fracture mechanics person here, so let me just very briefly indicate that in fact, you build fracture mechanics from 2 approaches. These 2 pillars support the foundation of fracture mechanics. Either you argue from the point of view of energy, Griffiths demonstrated in the case of glasses very successfully. Basically, eventually can attribute all the fracture strengths to the fact that certain energy has to be surpassed. So then there's also the second approach, looking at the strengths at the crack tip. But since the crack tip has stress divergence, one has to introduce remedy by saying that there is a plastic zone. At the end of the day, when you go to textbook, you read fracture occurs when G reaches GC, or fracture occurs when K reaches KC. In the case of KC, we really don't know what determines KC, but luckily we know that KC is related to G, K is related to G, therefore everything falls back to how to compute for G. Well, so far so good, except when we look at our polymers, much has been discussed on PMMA, polystyrene, you find this G, unlike what Griffiths likes to argue, is actually much larger than surface fracture. Okay, thousands, or if you use my estimate, even more larger than a fracture surface energy. So this makes the argument very problematic in terms of what insight we can have. In fact, this being much larger would imply that you actually have no quote-unquote nucleation barrier, meaning this fracture should occur at any level of crack size, because this line basically goes to 0. You only have just this line, this term dominant. Well, it looks very problematic. In any case, nevertheless, we have marched on, and there were books written on polymers, and many experts have been working on this. So I'm just a newcomer trying to learn what's happening as a beginner. So I have a lot to learn from you folks who know well fracture mechanics. So let me just entice you intriguing you with these issues. You find for plastics or elastomers, you find basically yeah, so you basically find that the strength of your polymer is much smaller than theoretical values for both plastic and elastomers. And then for the GCs, the toughness, our estimate is the theoretical ones is much smaller than the experimental. So what's going on? I mean, this is just looks crazy, right? So shortly, I can tell you based on our work that I'll show you next slide, that this happens because the theoretical strength was wrongly estimated. It's not that people doesn't know, but the question is, how do we estimate correctly? In the case of elastomers, the strength of polymers of elastomers is wrongly estimated, that we know, because everyone knows the low bearing strengths do not break at the same time. Okay, but we don't have a good model for what that strength should be for elastomers. So what about the second question? Since theory doesn't agree with the experiment, then there's a question of what is wrong with the theory. So how should we model the theory of GC and in both cases? So I briefly indicate that in the case of plastics, we have worked out a model that describes how the inherent strengths could be related to the structure of the chain network. And turns out that much of the network can break down below brittle ductile transition through chain pull-out. So it turns out that you could estimate the strength of your polymer, which is actually indeed a factor of 100 smaller than the theoretical limit, which doesn't occur, which is to say all the bonds bear load and all the bonds break. So this is our old work, so I'm not going to show you more. So let's move on to the fracture mechanics. I have introduced you the idea that we know what is the strength of polymers. If you open any textbook, we were indeed confused by this. We know that when you have a big cut of your polymer, you know your strength is inversely proportional to the square root of your cut size. That's classical fracture mechanics, that's this. But the same thing I raise in any book is why GC is 3 order magnitude larger than the theoretical estimate. On the other hand, how come this relationship works as if fracture mechanics work very well? So the past is summarized by this book by Kinloch, basically suggesting the flaws is always the reason for the problem, especially for the fact that the theoretical strength is different than the nominal strength. So we are actually keen to find out whether the theoretical strength is indeed much larger than the nominal strength. So we decided to look at Birefringence. It's a beautifully simple technique for this particular problem, because this particular problem is really a 2-dimensional problem. So all the principal axes are in the plane of your sample, so with the third principal axis perpendicular to the sample. So you can validate Birefringence as a way to report local information about stress. And that's what we do. In fact, the whole idea was to take an uncut sample, like this movie shows, and you build a relationship between the color change, which is birefringence or retardance, and the stress. So there's a reliable correlation, as this 2 figure shows, largely linear between the 2 quantities, the stress and the retardance. So once you have that calibrated, you can really have a spatial information about how this birefringence builds up at the top. So let me give you 2 examples. One is for plastics. This has we have written a long paper. It has already been released, posted, available to the public. So if you look at the plastics, it has been done for of course, for PMMA exactly 60 years ago. It has been done, except we are going to look at a little differently. Instead of just trying to measure what is GC through its operational definition, right? He just have a different notation than the modern notation that we are using, except for the fact, except for the notation difference, he just measured the GC, and we were interested in what controls GC, what determines GC. That cannot be answered from this operational definition, by definition. So we'll look at the PMMA. It's rather challenging to do because birefringence of PMMA is rather low. So we have to use rather thick samples, but we succeeded in being able to resolve the distribution of birefringence at the tip and convert that back to stress and plot that stress as function, for example, of reciprocal square root of the distance to the tip. So this is the data. This data actually confirms a schematic plot like this. This plot looks somewhat unfamiliar to fracture mechanics because I have showed previously, I know it did it pretty fast, that that actually the tip stress was supposed to converge to a common value. But we show that at the lower stress, the tip stress is lower. And you can carefully take a look at the movie and be able to show that. So having learned that, we actually, my student, rather, Chaitanya, used different styles of cutting the PMMA and reported his tip stress in that stress saturated zone as a function of the operational definition of K. So he found that this tip stress correlate with K linear. Okay, so by dimensional analysis, this means that constant must be involving some characteristic length in this fashion, 1 over the length square root. And in fact, this relationship holds all the way to the point of fracture. Moreover, this plot shows that at the fracture, the tip stress, local tip stress, has reached a level which is essentially comparable to what you see in an uncut sample. So we are starting to be able to claim that the inherent strength is actually not much different than the nominal strength. Moreover, as I said, this relationship holds all the way to the point of fracture, at which I'm indicating that my tip stress is at Kc. So we end up having a relationship showing that the tip stress, which reaches inherent strength, is correlated with Kc through a characteristic length scale that indicates the stress saturation zone. So this formula, folks, it's probably useful for many of the talks that I have heard today. In other words, the K, what determines K? What we showed you through the example of PMMA, what determines K? It involves some kind of characteristic length scale, which is not molecular. Look, for PMMA, it's about a fraction of a million. Okay, and the inherent strength, what we know through nominal stress, we can measure it, and we have computed, right? In my JCP paper 2014, I have a rough idea of what that should be. It's not 17 gigapascal. I convinced myself. So in any case, moreover, that this is Barry's plot. And Barry's plot, as well as our data, which is in solid symbols, show a big spread, indicating Kc has a range of more than 50%, which amounts to GC have a range of 3 because they are square root related, a factor of quadratically related, if you like. So why there is a spread? Well, this formula actually is starting to answer that question, right? Because the inherent strength will not care how Barry cut his sample or how Chaitanya cut his sample. It will be similar, but this P might be different. So we'll get to that a little more later. In any case, we could look at this so-called fraction mechanical problem purely in the linear elastic region, even for ductile material. So our goal was just to find all the polymers that to which we can apply linear elastic fraction mechanics. So for PET, which is ductile, then before yielding, before the tip yields, we should still be able to investigate how stress build up at the cut tip. And you find a similar result. In fact, you could find the experimentally determined K, the so-called stress intensity factor, against the operational K. They are almost comparable in this case, because we use a rather large cut size. So in fact, we can borrow that result. This is just a movie showing the PET cutting. In fact, we can borrow this PET to illustrate the fact that the case changes because this stress saturation zone is different, depending on how we prepare the cut. So when you make a cut, you are naturally involved some damage mechanics to cause some natural bluntness in your sample. And that controls how stress builds and where it saturates. As a consequence, you build to different level of KC. So with that, I think we are quite close. We were at the end of the plastic part. They look like I certainly need to emphasize in what we know in fraction mechanics. I learned without theoretical modeling, we have a fracture occurring when K reaches Kc, G reaches Gc. Gc, Kc are given here. They are operational. They themselves give you a measure of what they are, but it does not tell you what determines their magnitude. Okay, and of course they are equivalent in the sense that Kc can be computed from Gc and vice versa. It's the same thing in that sense. Now, what we learned through playing with this Birefringence to learn about the stress buildup at the point of fracture, we learned that the Kc actually has some dependence on the material properties. In fact, we are explaining why Kc is a material parameter because the inherent strength is a material parameter. And this P is a natural length scale that comes into the problem when you prepare a cut in the sample. So it's in that sense, when we are dealing with glassy polymers, we have already dictated that your Kc will be more or less a constant, not going to change very much. But of course, Kc for glass is very different because the P will be very small. For example, for glass, it will be nanometer scale. In any case, this actually tells us that we should concentrate on finding out what is the inherent strength of our polymers, which is what we have done. So this is why we are entering fraction mechanics, because we have some insight about what determines the inherent strength. More interestingly, since they are related, you can even have an expression for GC and ask what GC is determined by. Well, it's determined by the same characteristic length, and it's determined by the energy associated with this inherent strength. Okay. And you can assign some specific intuition to what this P is. So let me just use my next 5 minutes to talk about elastomers. Of course, one can do elastomer in various ways. And so this is a movie showing a piece of elastomer in the first way, single edge nut. You can do a peeling, you can do pure shear. And the initial work after learning from what fracture mechanics is about is Reverend Thomas. He very cleverly thought about using pure shear as indicated here. The only length scale in the problem is the height of the sample. The other dimensions are much larger. In that limit, he was able to argue using the approach of so-called energy balance to compute for GC he argued that GC should be given by this last expression here, proportional to the height of the sample, indicating that this is only a matter of energy storage in the entire sample. This really is puzzling to me. I just have a hard time visualizing, understanding this, as if I have some trouble with this energy approach, energy balance approach. So we can now actually understand where this comes. It turns out where it comes from goes back to what we have learned from plastics. That is, the fracture is determined by the stress state at the tip. When the sample is very much higher, much taller, it turns out the stress build up much more quickly at the tip. Okay, so it turns out you are really struggling why this is doing that. So in any case, let's at least confirm it's doing that. So my student Zhehao made 3 samples, 10 times apart in terms of height. And he just go around and find where the fracture occurs and calculate GC according to relevant toughness. And here are the 3 pictures. Amazingly, he was able to see that no matter what is your height, the moment fracture occurs involve the same state of stress at the tip. So maybe I will do it later. This movie is not playing on its own. So this is just a pure shear movie that we can come back to and play. So in any case, we basically were interested in contrasting a single knot, single edge knot study involving different diameters, different cut lengths, and pure shear. Look at this pure shear problem. The tip stress converges to the same master curve if you insist that your K for pure shear involves the far load stress and the height of your sample. So this allows me to reach the demonstration of where relevance expression comes from. It turns out, without going into any details, the plastics for single edge notch or pure shear eventually involve a similar thing. In other words, the tip stress reaching inherent strength and your Kc at a fracture is actually involving a characteristic P. And you can argue very easily that the Revlin-Thomas expression can be shown to be inversely proportional to H because your stress is proportional, your tip stress is proportional to K. So in any case, at the end of the day, I'm happy to tell you that the Revlin-Thomas formula works because the stress argument is the reason it works. So you can also patiently calculate how or evaluate the stress build up, and you also find that there is a characteristic length showing the tip size. So these are just similar results showing further confirming the result. And the reason we figure out that the prefactor is 1 is we compared pure shear and the single edge notch. By comparing between them and at fracture involving the same inherent strength, you could indicate that the prefactor is unique. So with that, I think I'm reaching the end in terms of a summary through this birefringence. Well, looking at the tip, we're not only look at the tip stress, we're looking at how the stress build up toward the tip and reaching saturation as demonstrated here. And this gives rise to meaning about what determines Kc. And of course, that also means we know how GC is determined by. It's related to the strength. It has to do with how how blunt the cut is, or how the material responds during fracture in terms of a natural length scale coming into the problem. So with that, I reached the conclusion. Basically, we set out to find out that essentially the inherent strengths and nominal strengths are similar. Therefore, this problem of fracture in our glossy polymers is not really a problem of invisible flaws making it weaker. It's not weaker, it's just what it is. And we have, for our polymers, have to find out what determines this inherent strength. And the mystery right now is, of course, this characteristic scale P. We still have very little clue about how the damage mechanics determines the magnitude of this length scale P. But the good news is we know what KC and GCs are in terms of what determines it. Okay, I'm done.